This cylinder is well, like 200 cubic inches is how much so if you need to expand this way, the height is you take this off and you expand this way.
Okay, suggestions for problems to talk about from the homework? What? 18. 18? Then you're saying 18. Is there one more?
12.
So 18 and nominations for a second problem? I've heard 12. $18 was a standout? Let's just do 18. Okay, so we'll do 18. So fold it up, get your right heading on there. Perfect. Okay, so which of 18? Did you have 3 to do? Was it 3 or 4?
4. A, B, G, and H.
A, B, G, and H. Okay, so which? I gotta do 2. We'll talk about 2. G? G and H?
Sure.
G and H it is. So we are looking at 4 things. Roots, y-intercept, vertical asymptotes, and end behavior. End behavior, okay? So let's start with G, and we'll do roots, or x-intercepts. $11. Right?
Yes.
Okay, y-intercept. What do we do to find the y-intercept? Yeah, so the y-intercept on the y-axis, x equals 0. So mathematically, that's what we do. We do x equals 0, and we get the y value, which is a negative 11/6. Is that right? Okay, vertical asymptotes.
2 and 3.
So we need to
Factor.
factor x minus 2, x minus 3 factors that. Is that right? So our vertical asymptotes, places where it's undefined,
2 and 3.
x equals 2, x equals 3. End behavior. What is it we do to analyze the end behavior? So we don't have a leading term because it's a ratio of 2 polynomials, right? So we find what's called the, remember what we called it? Effective. So like in effect, what is the leading term of this ratio in effect? And how did we find that?
2 leading terms.
You take the leading term of the numerator and the leading term of the denominator, and you find that ratio. Because as x gets very large, the leading term here will dominate, and then as x gets very large, the leading term here will dominate. So in this case, our effective leading term is x over x squared, or 1 over x. So as x goes to infinity, whatever 1 over x does, that's what k will do, the function k. So k will go to 0. That's what 1 over, so for very large values, 1 over a very large value goes to 0. As x goes to negative infinity, k goes to also 0. And then we want to sketch. So I'll just do my best here. I've got some room. Over here. So I'll sketch it over here. So we're going to do what was our root? Our root's 11. We have a vertical asymptote at 5. We have a vertical asymptote at 6. 2 and 3. Same difference. Picture's still good. All right, so just not to scale anymore. All right, so here's 2 and 3 and 11. Okay? Not to scale, but the overall picture looks the same. Y-intercept, around -2. As x goes out to infinity, negative infinity, it will approach 0. See, there's no roots here, so it's going to have, and if it goes through that y-intercept, it'll have to approach 0 from underneath like this. Because it will never cross the x, there's no roots here, because we only have that one root at 11.
So how do you determine that?
Okay, so then,
That's what's confusing. That's what I can understand.
the effective leading term is the ratio of the leading terms of the two polynomials. You take the leading term of the numerator and the leading term of the denominator, set up a ratio, that's x over x squared, and then simplify it. You know. Okay, so then the sketching is a little less important. Identifying all these parts is the essential thing. So I'll just go through the sketch fast. There are no roots here, and it goes to the y-intercept, and if it approaches 0, it must come from underneath like this. It never touches the x-axis over here. So it must approach 0 from below like this. Okay, then also there's no roots here, so we know as we get close to a vertical asymptote, it either has to go up to positive infinity or down to negative infinity. So it must go down to negative because there's no root here. It can't cross. Okay, so then from this side, it's going to go up to positive infinity. Again, there's no roots here. There's no roots here, so what does that mean? It means that it must, somewhere here, it must curl around and go up to positive infinity on this side of this vertical asymptote. So you got to use the fact, not only use the roots, but use the fact where the fact that there's no roots to make decisions here. Okay, so then from this side, it's going to go down to negative infinity. So this side's positive, this side's negative, and it goes through this root. And then what happens as x approaches infinity? It goes to 0, so it's going to have to bend back down and approach 0 from this side like this. So this is 11. This is our negative 11/6. This is our 2. This is our 3. So I went fast. Any questions about that?
Is it going to go up high above the x-axis? Does that line go?
We don't know. There's some maximum, you're right, there's some, just like there's some minimum value here that doesn't make it to 0, there is some maximum value where it's going to have to dip back down to go to 0 at infinity. We just don't know what it is. So the domain is all possible x values that are valid in this function. So really, in this case, it's a question of which x values are not valid, and then we'll take everything else. So what's not valid here? 2 and 3. So values of x that make the denominator 0, we toss those out, but then every other x value is okay. So for any other x value that I choose, any x value, I get a y value. The only place I don't get a y value is at 3 and at 2, where you're trying to plug 0 in the denominator, and you can't divide by 0.
So how do you express that?
How do you express that? So it's going to be everything from negative infinity up to 2, not including 2.
Not including 2. Then it's 2.
Starting at 2 to 3, not including 3.
And then
3 to positive infinity. So that's how you can express the domain. Okay, granted, I didn't talk about domain in class, so in terms of grading, you won't be responsible in terms of grading for that. We didn't talk about it.
Is that how you have to notate it, though?
There are other ways, but that's kind of the common way to do it. So you could also say, in this case, you could say all real numbers, x not equal to 2 and 3. X is a member of the real numbers, x not equal to 2 and 3. That's another way to do it. Okay? Other questions about this one? So h, let's just talk through it. I won't write everything down. What are the roots? 0 and -2. Roots are values of x that make the numerator 0. Okay? Vertical asymptotes. That's the denominator. -1/4. X equals -1/4. We'll give you a vertical asymptote. Okay? End behavior.
Isn't it just 1/4? Because you would add the 1 to 0.
No, you subtract.
No, you need to get a 0 in the denominator. So it'd be, you need to make that -1, right?
4x plus 1.
Okay, let's do it. 4x plus 1 equals 0. 4. It's a plus sign. Does it not show up on the screen?
It looks like a minus.
It's definitely a plus on my screen.
Okay. I see it here on my paper, but up there it just kind of looks like a minus almost.
It has a faded vertical, yep. But it is a plus. So then -1/4. Vertical asymptote. Y-intercept. Whenever you have a root of 0 or an x-intercept of 0, that's going to be the y-intercept too. So if you plug 0 in, you get 0. Okay, finally, end behavior. So what's the leading term of the numerator? X squared. Leading term of the denominator? 4x. Therefore, effective leading term is x over 4. As x approaches infinity, what will p do? So now we actually have an x in here. It'll be infinity, right? As x gets very large, so will y values, or p. As x gets very large, negative infinity. So the end behavior, effective end behavior, or it will be like this, will be like this. And then all the other stuff, the roots, asymptotes, y-intercept, fills in the middle, what the middle looks like. Okay. Any more questions? Yes, ma'am? The x-intercept, those are the roots, right? So values of x that make the function 0. So what values of x make it 0? Any value of x that makes the numerator 0. So 0 and -2.
And then the domain of this one.
Everything but -1/4. Everything but -1/4. Okay, got them passed in? Last chance. Okay. So I want you to open up to page, or on to module 7.
Cruising.
Yeah, we're cruising, right? And we're behind. Can you believe it? So, it's been my, I think it was important to not go any faster than we did, right? So I really want to make sure we understood stuff. So we're going to do on page 267, number 2. But I want to kind of set this up for you, okay? Because it's kind of vague in its directive. So a chef at a local restaurant wants to design a pizza cutter that will cut his, and let's change this to 19 centimeters. So change it from 11 inches to 19 centimeters because
Is that how big your pizza is?
it's going to work. Come on, work. Oh, I'm in the way.
That's you.
No, I don't want to freeze. Okay, so because all right, because that's the size of this one, 19 centimeters diameter, okay? So change it to 19 centimeters. And it says he wants to design a pizza cutter to get the pizza into 9 equal pieces. So the idea of a pizza cutter, it's kind of like a cookie cutter, all right? So it's not the most realistic thing, but here's the idea, okay? It's like this. It's like how does he design a pizza cutter to get 9 equal pieces? It doesn't have a protractor, nothing to measure angles with. So should his pizza cutter be like that? Should it be like this? How can we exactly get what this pizza cutter should be like so that the pizza can be cut into 9 equal pieces? Does it make sense? This is really what we brush our cat with. But it's exactly what they're talking about, so I thought this was good visual. Okay? So take a couple minutes. Can you cut up? How would you design a pizza cutter like this to get 9 equal pieces? Go. Talk about it.
It's pi to the diameter times pi is the square.
You guys are all talking. Why does one talk and the other?
19 times pi will give you
Okay, so and then the focus is not on formulas and remembering a formula from the past, but the idea is that you're given, let's see here, I need to go back to this. The idea is that you have things like tape, scissors, string, a ruler, what other kinds of things, like desk supplies.
What are you eating this pizza? Where are you cutting this thing?
No, you're designing the cutter. You're designing the cutter. You're not, so we got the pizza. It's 19 centimeters. It's done. You're designing this cutter. How are you going to design this cutter? Not with formulas, but with kind of desk supply kinds of things. How are you going to design this cutter? Okay, go.
Someone would be like, you want to take a That's my instinct. You have to divide it. Yeah. I thought my prior wrong, but I said take 1/9 of the circumference.
1/9 of the circumference. So that would like give you the length.
Or that would tell you how yeah, it would be the angle that each slice has to be.
Well, think about it. There's this one angle and this is the same angle. Like you can cut the pizza so it looks like this, or you can cut the pizza so it looks like this.
No, we're getting into like, are we getting into like the right angle triangles where like A squared plus B squared equals C squared?
It won't be right here because you have a curve. Pizzas have curves and that's true.
But you can divide this into 4 and then use that's right and then that's equal whatever I'm trying to say.
How are you gonna cut it
And then
half
you got-
like that? Because you need 9 pieces. Can't possibly cut it.
No formulas. Use desk supplies.
Desk supplies. He wants to
No formulas. No formulas. The things I listed. Tape, scissors, string, ruler. Okay?
So no circle walls.
No formulas.
No right angles.
Wrap it around. Cut it. Scissors.
Okay.
Right?
But then
That'll
what do you
give
do
you
to string?
That'll give you. Unroll it.
The length, which is the diameter.
And then you take your ruler.
You measure it. So that's gonna give us ours length.
Right? Or circumference. Equally length pieces of your shirt.
A like
Okay. Let's see what. Okay, so down here in front, I heard they come up with a good idea. So, anyone in the back or in the middle? Did you come up with how to do this? How can we design this thing so we're cutting exactly 1/9 or into 9 pieces? What do you want to do? How's this going to be possible? Yeah.
you tape it down. So they can
Figure out the circumference was through the diameter, the radius, whatever. Then divided that by 9, you would figure out how, like, the crust, how long the crust needs to be for each piece.
Okay.
And then the radius is going to be 9.5. So 9.5
Okay? So she's talking about the distance around, the circumference of the pizza. Will that help us design this cutter?
Yeah.
Will the distance around help us to design this thing?
Makes sense, yes.
How can we get it? How? How find the circumference? Yeah. I told you, no equations are off limits. Use a string. Okay? Or use curling ribbon, because it can fit around this pizza better. All right, so I'm going to take this, I'm going to fit it around. What's that? It's right here. Okay, so I'm going to take this. It worked great earlier. There we go. How did I do? Pretty good? So I got the distance around.
Sort of.
What am I going to do with that? How's this going to help us to design a pizza cutter for 9 equal pieces? Divided by 9. Okay, so what I found was that's 60 centimeters. That's 60 centimeters. So what are you going to do next? It's 60 centimeters around that piece of that pizza. Tell me. Divided by 9. I had to bring my ruler. 6.67? So 6.67. So if I mark off 6.67 centimeters, is it showing up? And then then my pizza cutter is going to be based on that arc length, right? Based on that arc length, so that we're going to make the corner of that vertex at the center of the circle, and then have it so that it's based on that arc length of 6.67 centimeters. And then I can just keep repeating that once I have that forged and set.
But you do have to then go into like the center of the pizza as well, right?
You have to be at the center, that's right. Yeah, so someone said 19, take 19, divide by 2 across to get the center. That's right. Okay? So, what is the point of this? The pizza cutter represents what kind of thing? And what is that representing? Like this opposed to this as opposed to this. What's the element here that we're representing? Angle, right? Angle. And so angle measure, here's the big point. Angle measure is based on what? Say it louder. Arc length. This is the basis of angle measure, arc length. Okay? And we're going to start by measuring angles just as fraction of one rotation, or fraction of a full circle. So what will this arc be called if we're talking about, what will this angle, what will we measure this angle as, if we're going to measure it as fraction of a circle? What will this angle be? What's that? 1/9. This angle will be 1/9. So this is our, is that showing up? I don't carry pens and pencils anymore because I got the thing. Here's the show. Got a pen? Can I borrow your pen?
Oh, yeah.
That showing up better? A little bit. So we're going to call this angle, could be 1/9. Fine, so what is 1/9 in the calculator? So let's write 1/9 as a decimal. 0.1111. Okay? You can also represent that as a percent of the circle. So this is going to be our basis for measuring angles. Angle is 1/9. Okay, or 0.11 fraction of a circle, or 11.1% of a full circle. That's the measure of this angle. Okay, so what would a measure of, so draw a measure of 1/4, an angle of 1/4, and then compare it with the person next to you. So draw an angle that has a measure of 1/4. What would an angle measure of 1/4 be?
Do you still need the pen?
What's that?
Still need the pen?
Yeah.
Oh, thank you.
Sorry. Okay, 1/4. What percent is that? So you could also say that as a percent. What percent? 25%. Or 0.25. How would you describe that angle? An angle of 1/4 or 0.25. You called it a right, is it a right angle? Yep, 1/4 be an angle like that. That's that angle. We're going to start by calling it 25% or 1/4. All right. How about, let's say, 67%. What fraction of a circle is that? About 2/3. So I want you to show that angle. So here's the angle of 1/4 or 25%. So show an angle of 2/3. How would we show an angle of 2/3? What angle is this right here?
That's half.
No, just in terms of percent of the circle. Half. This is 50% or a half. Okay? So we need to break it up into thirds, right? So thirds would look something like this. So what would a 2/3 angle be? If I started here, 2/3 would be that much. Okay? So in these cases, so we're really talking about the fraction or percent of the circumference, arc length. So 1/4 of the circle. 2/3 of the circle. So there's 2/3. There's 1/4 of the circle. So that's what it's the arc length that the rays of the angle cut off. The arc length that the rays cut off. So you'll see in the book, it'll use this word subtend. In the homework and in the worksheets. Subtend just means cut off. Cuts off. Subtend means cut off. So the angle subtends an arc length. So the angle of 1/4 subtends an arc length that's 1/4 of a full circle. The angle of 2/3 subtends or cuts off an arc length that's 2/3 of a full circle. So when they that's what this word subtend means. Okay. All right. So now let's look at something. If angles are measured in terms of arc length, then can you see 3 circles there?
It's very, very faint.
Let's try this. Better?
Yeah.
This might be too much. I hope not. Yeah, it might be too much. Let's try something in between.
Too much.
Well, because there's stuff that needs to go on top of it that you need to see. So let's try.
Do white. I think that'll work.
That's good. Okay, green. All right. Okay, so here's 3 circles. What am I representing by the purple bar right there? What am I representing by the purple bar?
The radius of the first circle.
The radius, right? The radius of, and what is that radius? Okay, so what I'm going to do is, I'm going to take that radius of 1, and I'm going to peel it off and lay it on the circle.
Interesting.
Did you see that? Want to see it again? Okay, so I'm taking the radius. Well, it's important. So I'm taking the radius, peeling off the radius, and wrapping it on the circle. So that's an arc length, right? So there's some angle associated with that arc length, right? Okay, so now I'm going to, what am I representing here? Radius of second circle, which is, what is the radius? 4. The length of that bar is 4. It's the radius of the second circle. Same thing. I'm going to peel it off and put it on its circle. What am I representing here?
The radius of the third circle.
Radius of the third circle, which is 6. Let's put it on its circle. So what I want you to tell me is, or talk amongst yourselves, what's different about those 3 arc lengths, and what's the same? And when you and try to think of 2 things besides color. Okay, so color doesn't count. So name 2 things that are different about those 3 arc lengths, and 2 things that are the same about those 2 arc lengths. Okay, talk amongst yourselves. 2 things that are different, 2 things that are the same.
We're supposed to go say 3 things that are different about each part. Let's go on to 2 things that are similar.
Similar would be the amount on each circle that's what would be the ratio of the dark to the light.
Okay, so let's start with the easier ones. So differences. The purple, the blue, and the red arc lengths. What's one thing that's different about those? So maybe start with the easy. The actual length, right? The length of the purple is 1 unit. The length of the blue, 4 units. Length of the red, 6. Their lengths are different. What's another thing that's different about them? Yeah. Okay, yeah. So how far away they are from the center? How far is that arc from the center? 1. How far is that arc away? 4. 6. Good. Anyone think of anything else? Got something else? Yeah.
Are they proportional to their arc length? Like each line?
Okay, yeah, so you're onto something there, definitely. So what else is this? Are we doing different or the same? So that's more like what's same. So that's talking about the same. So now, what is the same about these 3? What's that? Do they all give the same percent of the circle? And we said that that's our basis for what? Angle, right? So they all have the same. Let's see here. This. Oh, that's N, right? Come on. There we go. So if they all have the same percentage of the circle, of a full circle, then they're all marking off the same angle. Is that right? Okay. So if arc length is the basis, then we can use a radius of a circle as one way to mark off arc length and to measure angles. And so since it's based on 1 radius, this angle measure is called 1 radian. Radian. So what is a radian? A radian is the measure of an angle whose rays would subtend what arc length? One what? One radius. Does it matter if we're talking about purple, blue, or red? No, because they're all one radius. So one radian is the same here, here, and here, because it's the angle whose rays would cut off or subtend one radius of arc length. That's what one radian is. What am I representing here?
2 radian.
Okay, so if I told you that this right here was another radius length. So from there to there, that's another radius length. So what about this angle now?
2 radian.
Yeah, so from here to here, the first one we had stopped there, that's our 1 radian. So now, starting in the same place here, the x-axis, so this blue arc is how many radius lengths long? So its angle is 2 radians. I'm going to tell you that. So here's that 2 radian mark here. Here's another radius length. From there to there is one more radius length. So what angle am I showing now? 3 radians. Okay, here's what I want you to do with this 3 radians. For each purple, blue, and red, I want you to make a little chart. And I want you to tell me what the, let's see. So arc length we call S. So S is for arc length. Okay, R is for radius. And then theta is our kind of standard for angle measure. And now, and we're talking about in radians now. So we'll relate this back to percent of the circle in a second. But now we've introduced this new way of measuring angles according to arc length of using the radius. So you're going to make a little table for each of these 3 right here. Find the arc length, the radius, and the angle measure. So you're filling in 9 spaces in the table. Is the task clear? And then talk about it, compare with the person next to you. So now we're showing 3. So for the purple, what's the arc length? What's the radius? What's the angle measure? For the blue, what's the arc length? What's the radius? What's the angle measure? Same for the red. Fill them all in.
At this point in time, right now.
At 3, yeah, this angle. For the situation I'm showing right here.
So you see like 3S with that E.
They're all values. These are all going to be numbers. For the purple, what is the arc length? How long is the purple arc length? What is the radius for the purple? What is the angle measure? Described by that purple. Okay.
So angle measure, would that be like 3 radians?
Radians. In radians.
This is easy, guys.
Yeah, it's easy.
It's actually really easy. So
You just got to know what those 3 things are.
the arc length is at 3 radians, so that would be the third, that'd be your angle measure. Your radius is whatever the circle is. Your arc length is the radius times 3 times the radius. You got it? I got it. You got it. You got it. Are you okay? I'm fine. Don't hit me. I had to write. I had to write.
And then if you're done, you guys. If your table, you just filled it in easily. So then we're asking, the whole point of this is what's the relationship between S, R, and theta. Take one more minute. Okay, what is our arc length for the purple?
3.
They're saying 3. Is it 3 units long? 3 units, that's it. What's the radius? 1. What is that angle? 3 radians. Okay, blue. What's the arc length? She wants 12, agree?
Yes.
12. What's the radius? 4. What's the angle? Red. Okay, she wants 18 as the arc length. Agree with that?
Yes.
Radius?
6.
6. Angle. So what is the relationship between S, R, and theta? How are those related, those quantities of arc length, radius length, and angle? What's that? She wants S is theta times R.
Yes.
Okay, because what is this? This can be thought of as arc length, but measured in what? In terms of arc length measured with, yeah, say it louder. With the radius. We're measuring the arc length with the radius. So this is the number of radius lengths cut off by the rays of the angle. So if we multiply that by the length of the radius, it makes sense that we'll get the total length of the arc, right? Because this is measuring how many, this is the length of one radius, this is how many radius lengths. So this is then the total arc length. Okay, so really important. So everything we do in Module 7, which is our trigonometry module, so everything we do in trigonometry comes back to angle. So that's why we're really taking this slow. We really want to understand angle. So let's keep going. So can I erase everything on the screen right now? This was that relationship. Arc length will be number of radius lengths times the length of one radius. Makes sense. Oh, didn't want that. Come back. There we go. Okay, so I'm going to keep going. So let's actually, I want to zoom in, not zoom out. So this is 3. So this is our 1. This is 2. This is 3. I'll keep going. There was 4. There's 5. There's 6, right there. So how about these, when we wrap the radius on the circle, do we end up at nice symmetric places on the circle? We sure don't. Okay? We sure don't. So it would be nice to think about what would be exactly halfway across, halfway around. So exactly 50% or half of the circle. So can you make a guess at what that would be about? $3.5? 3.9? No, it's going to be close to 3, right? Some of you know because it's close to 3.1. So did you ever know what pi meant? You did. You knew it was the number of radius lengths to get halfway around the circle? That's what you knew? Oh, good for you. But I'm sure many of you didn't know that. But that's what pi is. Pi is the number of radius lengths so it's 3 and a little change, right? So 3 radius lengths almost gets us there. We need a little bit more. That's what the 0.14159 on and on and on. So it's pi's number of radius lengths to cover half of the circumference. And so therefore it's the angle, that would subtend an arc length of half the circle. Okay? So therefore, what's a full rotation? So 2 of those. So 2 pi. Okay, and you can approximate that, but it's not exact with 6.28. So this is exact. 2 pi is exact. That's how you represent it exactly. This is, if you wanted to do a quick calculation, you could use this as an approximation. Because that's it's truly an infinite decimal. The exact value is truly an infinite decimal. So what percent of the circle then, if we're going back to our percent, what percent of the circle is 1 radian? Find out. So what percent of the circle is represented by the arc length of 1 radius? Go ahead, find it. What percent of the circle? Or what fraction of the circle is 1 radian? How would you find that?
So a quarter of it is pi 2. Of the circle is pi 2. Because it's half pi. So 1's pretty close to.
How would you get the fraction of the circle that is 1 radian? What would you do?
Close to pi. Which should be like 2.
Yeah. Is it 1 over 2 pi? Someone get that? That's it. So you take the portion over the whole. Portion over the whole will give you the percent. What decimal is that?
That was 2 pies.
If you got it, yell it out.
Not 1.57.
What's that? This is going to be, it should be a decimal value because this is a portion of the whole, right? 1 over 2 pi.
1.57.
No, you got to put the pi in the denominator. You're putting the pi in the numerator. Make sure the pi gets in the denominator. It's less than 1. What is it? 1.591. Okay, we'll leave it at 0.159. Okay, so what percent is that? About? About. Okay. Any questions? This is a really hard module, and I'm going slow on this. If it seems too simple, you gotta retain it because it's all about angle. This module is all about angle. If you don't really understand angle, which it may feel really easy to you, but in a day, in 2 days, if you forget all this and try to do the harder stuff, you're gonna be dead. Okay, so please take this seriously. I'm going slow for a reason.
So when you're looking for the angle of the first radian,
Okay.
you would basically do the 1 over 2 pi, you already know your radius is 1. So would it be like 1?
So we're talking about two different ways to express this angle now. So now we have two ways to express this angle.
So that angle is 15.9% of 1.
Of a full rotation of the circle. Of a full rotation of a circle. So we can call this angle right here 15.9%, or we can call it 1 radian. Those are both expressions for this same angle. Okay? All the way around, we can say is 100% or 2 pi radians. Both of those are expressions of an angle of a full rotation. Okay, we'll pick it up here Friday.